to The Explainer. Today, we're tearing down an absolute legend in audio engineering, the active Baxandall tone control circuit. You know, if you've ever tweaked the bass or treble on a stereo or dialed in a guitar amp, you've totally used some version of this exact design. But what's actually going on under the hood when you turn those knobs? How do we pull off that perfect balance of frequencies and voltage gain without just completely trashing the original signal? Let's get into it.
That right there is the massive engineering hurdle we're tackling today. Look, amplifying a weak audio signal without dragging a bunch of ugly noise and distortion along for the ride is already hard enough. But doing all of that while letting you independently boost or cut the bass and treble without those frequencies bleeding into each other, man, that takes some seriously elegant, precise analog architecture.
Enter our solution, the active Baxandall tone control circuit. Specifically, we're zeroing in on an op-amp, or operational amplifier-based design. Now, the absolute magic here is in that word active. See, instead of just using passive resistors and capacitors that literally bleed your signal dry, we're throwing an active feedback loop into the mix. That gives us the muscle to actually boost frequencies, maintain our overall signal amplification, and keep audio distortion incredibly low. It's a total game changer. Okay, let's dive right into this. We're going to trace the engineer's journey, starting with the Baxandall solution and the TL72 two-stage design. Then we'll hit the math for gain and frequencies, validate the whole thing with Proteus simulation data, and finally wrap it up with a real-world engineering evaluation. All right, sections 1 and 2, the Baxandall solution and the TL072 two-stage design. Let's take a look at the physical architecture and see how these components actually cure the curse of flat, lifeless audio. So build a mental map of this circuit with me. It all relies on two totally distinct processing stages, both living inside a single, high-performance TL72 dual op-amp chip, running off a dual 12-volt supply. First up is the pre-amplifier stage. It's set up as a non-inverting op-amp, and its one and only job is to lay down a fixed baseline voltage amplification. Basically, it pre-scales the input voltage before any filtering even happens. From there, the signal hits the active Baxandall filter stage. This is the absolute heart of the tone control. It's an active feedback filtering matrix designed to let you tweak the low and high frequencies completely independently using dedicated potentiometers. No muddying, no bleeding. Moving on to section 3, the math for gain and frequencies. Let's break down the math right now and explore the underlying blueprint that really makes this circuit tick. We've got to start with the voltage gain derivation for that non-inverting preamp stage. The formula for voltage gain, or AV, is pretty straightforward. It's 1 plus the value of the feedback resistor divided by the input resistor. So plugging in our chosen hardware, a 22 kiloohm feedback resistor and a 10 kiloohm input resistor, we get 1 plus 2.2. That spits out a final voltage gain of exactly 3.2. And that right there is the secret sauce, that resistor ratio of 2.2. Your feedback resistor has to be precisely 2.2 times larger than your input resistor. Why? Because that guarantees the loop delivers the exact amplification we need. This specific ratio is absolutely crucial because it perfectly counteracts insertion losses. Basically, it makes up for the signal drop that naturally happens when the audio hits the passive components later in the tone network. Okay, let's shift to the tone filters and see how the rest of this comes together. Over in the bass section, we're rocking 11 kiloohm resistors and 22 nanofarad capacitors. When you run that through the standard cutoff frequency formula, 1 over 2 pi RC, we land at a frequency of 657.9 hertz. So what does that actually mean for us? It means the bass control knob is only going to mess with the audio below that specific threshold. It lets you dial in those chest-thumping low frequencies, and it leaves the vocal mid-range completely alone. Zero mud. Now for the treble section, we swap to a 3.3 kiloohm isolating resistor and a 470 picofarad high-pass capacitor. Run that exact same formula again, and we get an insanely high cutoff frequency, 102.6 kilohertz. Now hang on a second. You're probably thinking, human hearing only maxes out at about 20 kilohertz, right? So why in the world are we setting it so high? Well, placing the mathematical cutoff way above what we can actually hear guarantees us a super wide, totally clean operational bandwidth. It basically stops phase distortion from creeping into the treble range we can hear, ensuring we get that absolutely crystal clear high-end sparkle. All right, section 4, Proteus simulation data benchmarks. Doing the math on paper is great and all, but now let's plug this into our virtual test bench and prove that it actually works. Let's analyze this consolidated AC transfer function graph data. We're tracking a 1-volt peak-to-peak input signal across the entire human hearing spectrum, right from 20 Hz up to 20 kHz. Notice the incredible channel independence going on here? See how cranking the treble state up to 50% leaves the deep 20 Hz bass completely untouched, matching the neutral state perfectly at plus 1.36 decibels? That is the high-pass capacitors doing their job, successfully blocking low frequencies from sneaking into the treble feedback loop. Bottom line, adjusting your highs won't accidentally ruin your low end. Let's really anchor on that neutral baseline at 20 Hz. When you have the tone controls perfectly centered, meaning the circuit is electrically neutral, the system outputs plus 1.36 decibels. That right there proves our initial math was totally spot on. The gain of 3.2 from the preamp perfectly counteracts those passive insertion losses we talked about earlier. It maintains a perfectly stable, unclipped line-level output from the exact millisecond the audio enters the circuit. Now, let's contrast that baseline with this number, minus 6.27 decibels. When we push the bass control to 50%, but leave the treble dead neutral, the whole low-frequency floor just acts like a perfectly linear attenuator. All the way from 20 Hz to 200 Hz, the gain drops so cleanly to negative 6.27 decibels. It establishes this exceptionally flat, beautiful low-frequency shelf. And if we look way up at the extreme high end of the data, across all the states, you'll see a minor reduction, or compression, in gain right there at the 20 kHz treble boundary. Now don't worry, that is not a flaw, it's actually a feature. That simulated roll-off perfectly mimics the internal open-loop limits of the actual physical TL072 chip. It essentially acts as a natural low-pass filter, which is just fantastic for real-world hardware stability. It actively protects the physical circuit from high-frequency parasitic noise and all that unwanted oscillation. Okay, Section 5, Engineering, Evaluation, and Audio Trade-offs. Let's shift into our final phase here and look at the inevitable real-world trade-offs of a design like this. Evaluating the hardware application leaves us with 3 huge takeaways. First up, signal distortion. The TL072 gives you a crazy clean signal overall, but, and it's a big but, if you push that master gain too high, the op-amp is going to clip and your audio will seriously degrade. Second, stability. The dual-rail 12-volt supply paired with the active feedback network makes the circuit incredibly consistent, with virtually zero unwanted oscillation across the audio band. And finally, noise sensitivity. Look, the simulation is pristine, obviously, but physical hardware is a whole different beast. It is vulnerable. If you're building this, you absolutely need a proper PCB layout and really strict grounding techniques. Otherwise, external electromagnetic noise is going to totally infiltrate your system. And honestly, this brings us right to the golden rule of this entire project. Audio engineering is, at the end of the day, a high-wire act of balancing competing priorities just to achieve sonic harmony. You increase gain to amplify a weak signal, but hey, you invite noise. You boost the bass to add some warmth, but you risk muddying up the entire track. It's the careful, mathematical balancing of these active components that preserves the fidelity of the original signal, while still giving you, the user, complete control.